Okay, in this next to last lecture, we're going to cover urban coding, and specifically a new kind of coding called generative codes, and we'll explain a little bit more about that. It relates to what we were talking about with the way computers are moving away from the world of specification and into the world of generativity. Generate, don't specify, as my friend Ward Cunningham put it. And this is really changing the way that we're thinking about how to handle our design challenges. We're designing the process rather than the product. We're designing the code that's going to generate the outcome rather than the specific outcome itself. And so this is a real transformation in the ways that we're thinking about how codes are going to work. And so this is in some ways a frontier, you might say, of urban coding. Let me see if I can get this thing to go away. Hold on just a second. There we go. So there are a number of common coding approaches that I'm sure you're probably familiar with. The most common today in the urban world is Euclidean zoning or use-based zoning, which is the standard model in many cases. In this case, this example that you see here, it's specifying exactly what can go on that particular lot that's been selected. It's a residential single unit, a particular density, very prescriptive, very precise of what you can do on that lot. And this is actually creating a lot of problems because it is causing great rigidity in the ways that we can adapt to our problems like affordability and diversity and all the things we've been talking about. Dominic, are you seeing that okay?
Yeah, everything is fine.
Okay, good. And then, of course, there are the more familiar design codes that tell you more about what the aesthetics needs to be, what the form and materials and colors and so on of the building, not so much the urban form, but the building form, and particularly in places like historic districts when they want to try to ensure compatibility. And those can be quite prescriptive as well, talking about how you do particular details or whatever. And then there are the urban codes that are much more form-based. The idea of a form-based code is that you're not prescribing the use, you're actually liberalizing the use and allowing different uses to go in different places as long as the impacts are not being disruptive. And in many cases, you're just going to control those. If you have a factory, say, that's emitting caustic gases, then you want that factory to control the gases. You don't necessarily require the factory to move away, or maybe they just change the way they're doing their business. That's the idea of form-based codes. You're going to be much more prescriptive about how the building relates to other buildings and to the public realm, the position of it and the relation, the way it supports the street and the pedestrian experience and so on. This is an example from Seaside, the famous town in Florida that was one of the early examples of new urbanism. And again, a lot of folks focus on the style of Seaside and get kind of hung up on that, I think. And they miss something really important, which is that Seaside did achieve some really new landmarks in mix of uses, walkability, de-emphasizing the car, creating a much stronger public realm, and those were important milestones at the time. And this actually is a one-page code that they created for the town of Seaside. It prescribes where the buildings go on the lots, how they orient to the public realm, how they support the public realm with the frontage zones and so on. Very innovative for its time, very elegant and spare, only a one-page document. And then there are various performance-based codes that specify what the outcome needs to be, but not how you're going to get there. You're probably familiar with those when it comes to energy codes. Where you would have a prescriptive code, it might tell you exactly how much insulation you need, but a performance-based code is not going to tell you that. It's going to say you only need to produce this much energy loss or energy gain, and just show us how you're measuring that. And it doesn't matter to us what kind of system you design to achieve that, as long as you achieve that goal, that you achieve that performance. And then there are context-sensitive codes that are essentially form-based codes that are differentiated by the context. And the idea of this is that in different parts of an urban area, you're going to have different form-based coding requirements in the more dense urban areas and in the less dense rural areas. And this is a contextual approach where you recognize that you're going to have different kinds of form-based code depending on the context. This is just something developed by Andres Duane's brother, Douglas Duane, and it's really a contextual organizing system for urban coding. As I said, as Andres Duane says, it's the currency for negotiating the human place in nature. In other words, we're looking at how humans can be dominant in some areas and natural systems can be dominant in other areas. And there is a sort of negotiation between those, and that is the transect in essence. This came from the work of Patrick Geddes around the turn of the 20th century, early 20th century, looking at the ecological transects and how those might apply to urban transects or human settlements. And this is an example of how you might have a very dense urban core and then you might feather out into the landscape. That's the idea. And this is the idea that maybe the highest density zone, the most urban zone, or a T6 as they call it, would feather out to a T1. But it's not just a simple fried egg diagram. That's not the way natural cities are, and that's not the way really good cities are. Good cities and natural cities have a polycentric structure to them. You have nodes, you have clusters of density. You don't have only one big center. You have big centers, small centers, medium-sized centers, and the area surrounding them. And that's the idea, again, of a kind of fractal structure that exists in natural cities and in cities that spontaneously adapt to their natural requirements. Here's an example of a transect code where they went in and actually did that. There you can see the polycentric structure. This is in Florida. And the green area is the wetlands and the ecologically sensitive areas that they needed to stay out of. And then they created this sort of polycentric zoning system in the buildable areas as a result. And it's important to note that you don't always go from T6 to T5 to T4 and so on. You can jump from T6 to T2, an example of Central Park in New York City, or Hyde Park in London, or many other examples where you have discontinuities, and that is certainly allowable and likely to happen in many cases. Here's what a community plan looks like. I think that this is Sarasota in Florida, and you can see the different transect zones, and they allow many different things within each zone. It has, again, more to do with the form and the relationship to the street than with the use. And it tells you some things about how close you are to the street, what kind of furnishings you might have, how the buildings might vary in height and size and position. Again, the form, not so much the use. There's an example in the upper right of how that configuration might work and how it might actually lay out with the buildings on the street. And so the SMART code is Duane Platter-Zyberg's effort to operationalize this idea to create an open source zoning code that anyone can adopt in place of the Euclidean zoning or the use-based zoning that dominates. And there's many examples of where that has been implemented. And this is in the Smart Code Central. You can go to that website, smartcodecentral.com, and read some of this background material, going from the most urban to the most rural, and incorporating a transect of character and intensity, brings all the other elements, a lot of the boilerplate that overcomplicates zoning, into a much simpler kind of system. A model code that can be used as freeware, a template that can be locally customized. Again, it's a form-based code replacing Euclidean zoning. And it's a unified land development regulation. It can function in terms of the laws and the standards and the codes, the regulations. Again, that operating system for growth that we talked about yesterday. Most importantly, it's promoting walkability, the core principle really of sustainable urbanism, of new urbanism as a set of ideas, and certainly of the new urban agenda as well. That's a key part of it, a key part of the goals. And the rural urban transect. It's a modular structure. You can drop in different modules that address different concerns that might vary in different locales. There have been a number of modules that have been created for it. I've actually been working on a pattern language module, as a matter of fact, for the smart code. And very elegant. The core document is only 50 pages. Many design regulations are hundreds of pages long, or many many websites or many web pages on the internet. Again, I'm going to flip through some of this. You can see examples of this on the web. Here's where many of the smart codes have been adopted, or they're in, at the time of this writing, we're in process of being adopted. Looks like there's one in Poland, as a matter of fact. There are roughly 179 of these that are currently, or were at the time of this writing, another 500 or so that are other kinds of form-based codes that have been adopted as well. So this is coming on as pretty strong at this point, and beginning to change the way we're thinking about urban coding, getting away from the use-based zoning, the segregated functional segregation zoning, and creating that diversity that Jane Jacobs and many other theorists have talked about, and operationalizing it. And then I've talked a lot about Christopher Alexander's work, and I'm going to close with some of his ideas on coding. As he says in a paper that I was a co-author with him and several other authors, that we think that generative codes could be represent a new era in human reconstruction. And I'll describe why we think that and what some of the elements of it are. But going back to pattern languages, we talked about this before, that pattern language is a generative system like other languages, right? We talked about that yesterday. But there are clearly some remaining issues with the book. As Alexander himself described, there's not enough ability to customize. The original book is this Bible-like volume that has, if anything, been a victim of its own success. It's hard to interface with conventional modern systems and methods. There's not enough information about form and geometry. And Alexander thought this was a fatal weakness, actually, that required serious remediation. And he actually spent the next 25 years working on that particular issue, how to deal with form and geometry. And that was really what the nature of order was all about as a project. 25 years working to deal with these shortcomings and trying to understand how those insights could be operationalized. So I've talked about some of this work before, but I want to recapitulate it a little bit in the context of what we're talking about today. Remember that he wants to understand how nature achieves the order we see everywhere around us. It does not specify, it generates. It does not make little blueprints. It makes something more like recipes or codes that grow the form, that grow in a predictable way, something that is going to achieve the goals that we're after. But the results are complex, adaptive, and emergent. You can't quite predict exactly what's going to emerge. And we can learn from these processes and incorporate them. We've done so in the past, and we still do so now to some extent. But we can do a whole lot better if we take the lessons that are available to us. I talked about some of the key ideas, the idea of centers, that we can understand how regions of space can relate to one another as systems of centers or fields of centers that are interrelated in this sort of networked, connected pattern. And there are sets of sets or systems of systems that work together that are distinct. And the life or intensity of one center changes in relation to the centers around it. If you have certain centers that help other centers. And I gave this example the other day from, this is Penelope Cruz. And you see in a human face, this idea of regions that are distinctly unified into centers or, lineal groupings. Those would be centers too in Alexander's scheme. And of course, the iris and the eyelashes and all the parts of that complex biological structure that we can recognize and respond to and understand the centers and the symmetries and so on. And if you strip those away, something very disturbing happens. As you can see, you get this sort of doll-like, unlively, literally dead-looking automaton, almost quite a frightening looking thing, as opposed to what happens when you bring the centers back in together and bring them in with the nose and the mouth and the cheeks and so on, and into this whole structure that we recognize as a human face, and we respond to, as some, in her case, what we widely consider a beautiful actress. And that's the nature of human biology, to create faces that we can read and understand and respond to in various ways. Then there's this idea I touched on also of structure preserving transformations that he later referred to as wholeness extending transformations. And this relates very closely to the idea of symmetry and symmetry breaking. You can have a symmetrical structure that then shatters. This is Edgerton's famous milk drop, as we discussed the other day, but it doesn't turn into a messy blob. It often can turn into more symmetries, more complex symmetries that are related to each other in very complex ways. New centers with a series of geometric properties. And this is what Alexander observed in many, many examples in natural systems and in art. Levels of scale, strong centers, boundaries, alternating repetition, positive space, and so on, local symmetry, the kind of fractal structure, and so on. And you can see this in many natural systems and in many human systems, particularly in traditional architecture that's just loaded with these kinds of geometric properties. And he cataloged these, and he was able to get just 15 of them that he was able to describe as essentially forms of combinations of centers or regions in space, the levels of scale of the centers, the strong centers, the boundaries around the centers, the alternating repetition of the centers, the positive space, the good shape, and so on and so forth. And then thinking of that as transformation, these are not static structures, they're structures that are arising as the result of the processes, like you saw with the milk drop, that are spontaneously producing these geometric structures. And this happens in living systems and even in non-living systems, the beautiful ripples of a sand bed or the stains of water on a rock face and so on. Very beautiful patterns that we respond to innately, those sort of fractal patterns and the patterns that we talked about, biophilia, and we're hardwired really to perceive these and to find them pleasing, which is probably a good reason why we produce them so often. I have produced them in our traditional environments for hundreds or thousands of years. But if we take a different kind of form language that is more elementary, you might say, more based upon Platonic solids and cubes and triangles and cylinders and so on, then you're going to generate a very different kind of geometric structure. You're going to be very limited in the kinds of geometric structures that you can produce. And this is, I think, what Rem Koolhaas was alluding to when he talked about modernism's alchemistic promise to transform quantity into quality, to take just an elementary quantitative approach to geometry and just repeat, repeat, repeat. And somehow that's going to produce something satisfying. And he calls it a magic that didn't work. And he has said that we are now in this massive crater in our understanding of modernity and modernization. But what I would say is I think we can crawl out of that crater perhaps by understanding some of the new insights that are emerging from the sciences as we've been talking about throughout this course. And Alexander describes many of those. He talks about how, when you're doing an iterative process, a generative process, it's a sequence of steps that always begins by recognizing the initial conditions as a whole. It doesn't scrape everything away. It starts with whatever is there and embraces if you will, the grit in the oyster that can help to generate the pearls along the way. And this means that we have to diagnose what's there, we have to understand it and respond to it. Just as a doctor doesn't begin by just throwing you into a battery of tests and x-rays and so on. They say, hey, well, how do you feel? What is your complaint today? What's different about your life? And often that tells them what's actually going on, those clues, those qualitative evaluations by the patient. And these are really real phenomena. You know, you really do have a cold or COVID or whatever it is that you're telling the doctor about. It's not just your socially constructed attitude towards your health. And so this, for Alexander, means that there could be a different kind of operating system, as we've been talking about, to create urban and architectural form, a kind of generative code, a generative approach, not just parametric in the sense of, well, it's got to be either on this side of the line or that side of the line, but more like a bottom-up rule-based operating system or generative system. And I mentioned the work of Basim Hakim, who has done a lot of work on how often the codes of history have functioned as generative codes, and generating these very complex urban patterns like this one this is Ronda in Spain. And the idea also that I talked about that, Alexander talked about pattern languages as he wasn't satisfied with them as being just patterns of form, like static results, but rather thinking about patterns of process. And that's really what generative codes are all about, creating a kind of design build process, very much like a recipe or a traditional craft. And this is very much the issue that is the insight for generative codes, but you do have to deal with the legal requirements. I talked yesterday about the coding for an existing cadastral system where you have to create the lots and so on. You have the political requirements, you have to generate political will, and financial return. Obviously, if it doesn't pencil, you're not going to be able to build it. And that in turn requires changing this operating system, the operating system for growth. And so this is the idea that we proposed, that we could perhaps produce a scheme for generative codes that could really be something really exciting, could lead to something along the horizon. This is the paper that we wrote that was published in the book New Urbanism and Beyond. And you can see some examples of Alexander's work there, where he used generative coding and patterns from pattern languages to lay out various structures on the land and to essentially iterate and gradually evolve those structures, much like a crafting process, getting the bulldozers out there and survey equipment out there and so on, and producing some, I think quite interesting and quite lovely results. This is the Asian school in Japan. It looks kind of vaguely Japanese. It followed some of those Japanese patterns. And then I want to close with this really, I think, exciting frontier, which is the frontier of artificial intelligence and so-called neural networks. And you remember, we've been talking about Herbert Simon's work on nearly decomposable hierarchies and Alexander's idea of overlap, that you can't decompose everything into a nice, neat hierarchical system. You have to allow for the overlap and the interconnections between the variables. And Jane Jacobs, who talked about the web way of thinking, that we need to preserve the ability to have these interconnections. And in fact, that's how the human brain works, and how these neural networks actually work when it comes to AI. These are essentially remarkably powerful evolutionary systems that, without going into a lot of the detail, allow a system to essentially learn by trying out different combinations, many different thousands or millions or billions of combinations of pathways that can produce a remarkably sophisticated outcome, and often drawing on databases and data sets about what a cat really looks like. It'll go through millions or billions of images of a cat and millions or billions of images of a dog, and it will gradually learn that when you put a new image in front of it, that's a dog for sure, which is quite remarkable, quite sophisticated. And it's happening as a result of this web-like system, this web way of thinking, this web way of modeling that we've been talking about throughout the course. It's really remarkable what AI can do now in terms of how it can generate language in response to queries and be incredibly sophisticated. And there was a computer that won the Jeopardy game, and computers that won Go, and other things. Now it's getting to the point where these systems can actually carry on conversations at an extremely sophisticated level, And that's not just a toy. That can be very useful if you're trying to generate different outcomes that might be useful. If you're trying to solve a problem, and maybe the computer can help you to generate possibilities. And that is indeed what's going on in the design world. AI is being used in software. Space Syntax is using something called DepthMapX. And Unity 3D is built from software developed for game engines to enable designers to analyze their plans, like the shortest distance to fire exit, other sort of optimization things that the AI is going to help you by learning, by finding new ways to design. And that can allow you to rearrange or generate spaces in a plan. People like Zaha Hadid have put this to use, I would say, in a kind of razzle-dazzle way, not a particularly sophisticated way when it comes to human problem solving, but certainly interesting from an aesthetic point of view, a superficial point of view. And a number of people have done that. This is an example, by the way, of a AI-generated, very complex pattern, very interesting pattern that has a lot of those sort of fractal characteristics that we were talking about. And you could use that perhaps to generate ornamentation, to generate things that you actually want at a human scale in order to promote walkability and sociability and the other things that we need in our environments. This is a quote from that article. Someone is talking about, well, maybe we could have robot stonemasons who and this can be slightly ludicrous, but it could be interesting if, for example, you could explore the potential for form giving through spontaneously generating a building on site just from a sketch that could become quite sophisticated, actually. And that is now becoming possible. There's work that's being done in this field, a guy named Bruno Possel. And this is from my friend Ward Cunningham, who I mentioned before. This is an email exchange he and I just had yesterday, where he was talking about how fascinated he is by Bruno Possel's work, and I'll show some of it in a moment. Fully automatic generation of entire neighborhoods that Ward finds stunning. I share his excitement for its fitting of a small part of that work into present workflows using a software engine called Blender. And then he says, Ward says, we've got to be careful about what computers should do and should not do. And he talks about this paper, 10 challenges for making automation a team player in joint human agent activity. This is like, how do we control AI? Because there's a dark side to all of this, as we've seen with social media. But this is some of Bruno Possel's work, where he's generating entire urban layouts and building layouts that are quite intricate in terms of how they resemble, and more than superficially, the patterns of a traditional urban evolution, the way that urban evolution iterates and gradually twists and turns and does interesting deflection and so on. And you've seen that in, we've shown a number of examples of places like Rome and Ronda, Spain, I was just talking about. And you can actually get that quality now. You could have a group of people working collaboratively. You could have stakeholders participating in this and saying, oh, I like that, but do it more that way, and so on. So that's really interesting. And so, as I said to Ward, I like Bruno's approach that we perhaps write or import the patterns. Bruno is using the pattern language to help guide this process, quite interesting. And then get the software to generate some VR outputs that can then be evaluated by the designer, the stakeholders, et cetera. And they could look at a lot of historical examples using neural nets and evolve output that the designer operator could then select and manage, like looking at all the cat pictures and all the dog pictures and being able to tell, which one do people likely prefer or whatever. And an interesting idea would be to train the AI systems to write architectural and geometric patterns, to actually go to the other end of the generative process and write the patterns. And then the patterns could then be used as inputs. And then the humans could evaluate that and say, no, write another pattern that does this. And then they could do that and it become very sophisticated. And again, this is really far, far beyond what Chris Alexander dreamed of in his early days when he was working with computers back in the late 1950s and early 1960s, when he really began his thinking about pattern languages. And so we're just going to finish it in just a moment, and then we'll start the next lecture. But again, there's a cautionary note here that deep learning systems in general, it's very difficult to tell what's actually happening inside the model. How does the AI system know that it's a cat and not a dog? You can't really, decompose that into, oh, there's where it makes the decision, because it's a whole systems process. That's all the neural network functioning as a whole. And you give the program an input, it gives you an output, but it's hard to tell why exactly the software chose that output over others. And as I said to Ward when I was following up in this exchange, I said, I like the paper by Klein about how agents, AI agents could be collaborators with humans, but because neural networks working at any usefully large scale do act unobservably, how are we going to deal with that problem? In a sense, that's a problem that we all have as designers and as human beings, because we all have the sort of Freudian dimension of our behaviors. We're not necessarily aware of some of our deeper motivations and so on. We have bounded rationality and so on. But we have a system of conventions that tries to make up for it when we have manners, when we have, the ways that we behave with one another in civil society and so on. So maybe we need something like that for AI. Maybe we need something like Asimov's 3 laws of robotics. It's about how AI systems should not harm human beings. And so there's a lot of discussion about that. This Scientific American article that describes some of the pitfalls of trying to control AI. And then I think I was concluding with Ward, because Ward and Jenny Quillian are the other 2 board members of our nonprofit called Systasis, that I think we should work on this problem, the dangers of AI, as part of a larger problem of our technology and what's good about it, what's dangerous about it, what we need to do to reform it, including our design technology. And I hope this thing comes through the course overall, that we have incredibly powerful technologies today. We've transformed the world in so many ways, and yet we have limitations to those technologies. In fact, those limitations are becoming catastrophic when you talk about the depletion of resources, the emissions of greenhouse gases, the collapse of ecosystems, and so on. And this is partly manifesting in exactly that, the severe degradation of the biosphere, but also in the slow but steady erosion of cultural systems and their critical, if imperfect, capacities to promote well-being and even survival. And you see, for example, with social media and the rise of divisiveness, the rise of bitterness and contention, and people unable to solve their problems at the urban scale and perhaps at the national scale, and even to agree on what their problems are in many cases. And at the same time, there is a fundamental form of incompleteness of our knowledge, incompleteness of any knowledge system, any representative system of reality, going back to Kurt Gödel's work. That's partly inherent, but also it's partly manageable through self-correction, through this iterative process, and through what we have in our cultural system with peer review and ideally democratic processes where we're able to check one another, checks and balances and so on. But if we fail to self-correct due to our primitive understanding of the nature of our situation, then we're going to be in trouble. And I think that's what's going on, certainly in the world of urban planning and architecture. We need to recognize, as Jane Jacobs said, the kind of problem a city is, and be able to provide the right kinds of approaches, methodologies, tools, and so on. We need to improve our understanding and our ability to manage and really affect a transition. I think that's what's going to happen historically. It's going to have to happen to a more survivable kind of technological and cultural era. I think this is in many ways exciting, in many ways frightening, but here we are, and it's an amazing time to be alive and to think about all this.